Hello everyone, I am Prajwal Agarwal and today we are going to discuss this problem, black and white tree. This problem is rated as medium on CodeChef and you require experience in trees, DFS and dynamic programming to solve this. So guys, if you haven't read the problem yet, go back and read it and then come back and see the solution. With this, let's begin. In this problem, we are given an undirected tree with n nodes. Basically, we are given a tree with n nodes and n-1 edges. Now it is given that every node has a color. It can be either black or white. So 1 indicates white and 0 indicates black. So let us say in the initial configuration we have colors like these. Now it is said that we can choose any node U and we can toggle its color. So we can, if it is 0, we will convert it to 1, and if it is 1, we will convert it to 0. It is also given that when we change the color of this node U, then we have to toggle the colors of all nodes V that are connected to U using an edge. So let us say in this example, we select this node as U. So we will change the color from 1 to 0. Now these three nodes are connected to this node using an edge. So we will also toggle the color of all these nodes. Now in the problem we are asked the minimum number of steps that we need to perform such that all the nodes have color as black, which is all nodes have value 0. The constraints given to us are, we have test cases ranging from 1 to 5 into 10 to the power 4. N can range from 1 to 10 to the power 5. The color can be 0 or 1, and we have edges as x, y. This problem was asked recently in the contest Starter 15 and less than 10 people were able to solve it in Div 1 and Div 2. Now let us move on to the test cases to better further understand the problem. In the first test case, all the nodes have value 0, indicating that all the nodes are black. So we do not need to do anything, and the answer is 0. In the second test case, we can perform the operation on node 1. Hence the colors will toggle, so this gets converted to 0. Since 2 and 3 are connected to 1 using an edge, we will convert the color from 1 to 0. Now all the nodes have color 0 and we did one operation, so the answer is 1. In the third test case, we can perform the operation first on node 3. This will convert 0 to 1 and this 0 to 1. Node 2 is not directly connected to 3, hence we do not change its color. Now we perform the operation on node 1, which will convert this 1 to 0, this to 0 and this to 0. Now all the nodes are colored black, indicated using 0, and we did two operations, first on 3 and then on 1. So the answer is 2. So guys, now let us look at some of the observations to approach the problem. In this problem, we are given a tree with each node having a color and we want to make all the colors as 0. So the operation that we can perform is we convert 0 to 1 and vice versa. So since we are only toggling between 0 and 1, it does not make any sense to perform this operation twice on a single node. For example, if we choose this node 3 and perform this step, then 0 gets changed to 1, this gets changed to 0, this toggles to 0 and this toggles to 0. Now if we again choose this node 3, then this will toggle to 0, this will toggle to 1, this will toggle to 1 and this will toggle to 1. As you can see that after performing the operation twice on a single node, all the original colors have been restored. So doing an operation twice on a single node is same as not doing it at all. Moving on to the approach, it is pretty much clear that there is no obvious greedy solution. Hence we will use a dynamic programming solution to solve this. Another clue to use DPA is that it is an optimization problem and DPA is very helpful in these kinds of problems. So we will use a bottom-up dynamic programming approach to solve this. This means that we will first solve for all its children and then we will compute the answer for the parent node U. To get a better idea of the intuition, let us say that every node can be toggled or not. So we can choose the parent node and we have choice that whether we toggle this or we do not toggle this. If we toggle this, then we will pass the corresponding values to its children and we will solve for its children such that the whole of the tree is black. And if we do not toggle this, then we do the same thing. We pass those values to the children and we solve for all the children such that the whole tree becomes black. The complexity is 2 to the power n. Why? Because every node can be toggled or not. We will try to optimize this to using dynamic programming approach. Moving on to the solution. To apply a DP approach, we first need to define some variables that will uniquely identify the states. So, to identify all the states, we use 3 variables. The first is the index. Index basically is the index of the current node for which we are finding the answer. The second is the color value, which is C. This is the color value of the current node for which we are calculating the answer. The third is the toggle. This will tell us whether we applied the step on the current node or not, and this is equal to our answer. For example, let us say that we are solving for this current node u, then our answer is basically the minimum steps such that the color of u is C and the color of all its children C1, C2 and C3 can be denoted by C of I is black, 0. We need this toggle value because suppose we perform the operation on any of its children, then we need to pass this information to the parent as well because the parent color will also get flipped as we apply the operation on any of its children. Now let us look at another important observation that will help us figure out our transitions. So let us say that we are solving for node u and we have some children. Remember that when we perform an operation on children, the parent also gets updated. That means that the color of u will also flip. So let us say that the color of u is currently 0 and the toggle value is 0, which means that we are not going to perform this step on u. So the number of children that we can perform this step on is either 0 or it is 2 or it is 4, and similarly if we have more children. This means that if the color is 0 and toggle is 0, we have to maintain this 0 at node u, so we can only flip even number of its children. Meaning that when we flip even, this 0 will actually toggle to 1, then it will toggle back to 0 and go and so on. Similarly, in the second case, we have color as 0 and toggle is 1, which means that we perform this operation on u. This 0 will get changed to 1, and to convert this 1 back to 0, we need to the number of children we need to toggle is odd. We need to perform the operation on at least 1, and we can perform it on 1, 3, 5 and so on. Now for the third case, we have the color value as 1 and we are not going to toggle, which means we are not going to perform the operation on u. To convert this back to 0, we need to take odd number of children for the operation. So this is also odd. In the last test, we have color as 1 and toggle is also 1, which means that we will convert this 1 to 0. Hence, the number of children that we can take for operation is even, so that the whole tree is black. So this is also even. The parity of this is 0, for odd it is 1 and for even it is 0. Moving on to the solution, the first thing that we need to do is to calculate the required parity of children. Now this variable will tell us whether we are allowed to flip even or we are allowed to flip odd number of children so that u is black. Our goal is to make all the nodes of the tree as black, which is change all the colors to 0. So let us say for u the toggle value is 0 Now for all the children, we need to take the color value also as 0. This is because since we are not going to toggle U, we are not going to flip any of the children's. So the color of children should already be black. So to calculate the answer for dp of U, C and 0, we need to take dp of Ci 0, and the toggle value for children can either be 0 or 1. This will depend upon the required parity. In the same way, we can say that if the toggle value of U is 1, which means that we are going to perform this operation on U, meaning we are going to change the color of U as well as all the nodes of C1, C2, C3 and so on. This means that for Ci, we need to take the color value also as 1, because these values are going to flip and we want the final values as 0. So to calculate the answer for dp of U, C and 1, we will use dp of Ci 1, and the toggle value again can be 0 or 1 depending upon the required parity. Now to calculate the answer for U, we know that we have calculated the answer for all Ci's. So for Ci, we know all these values. So to calculate dp of U, C and toggle, where C and toggle belongs to 0 and 1, this is actually equal to summation of minimum of dp of C of I toggle 0 and dp of C of I toggle and 1. So basically we take the minimum of whether we toggle Ci or we do not toggle Ci. Now as proven above, if the toggle value of U is 0, then the color value of children has to be 0. Else if the toggle value is 1, then the color value of children is 1. So we copy this toggle value from U to the color value of Ci. Now we also need to calculate the parity of the children chosen such that their toggle value is 1. If that value is equal to the required parity, which we had calculated initially, then if it is yes, then we are basically done and we have our final answer. If it is not, then we need to select one more children whose the extra cost, basically the difference between Ci toggle 1 minus dp of Ci toggle 0. This value is minimum. For the implementation of the above solution, first we will create an array of size n cross 2 cross 2. This will basically store our answer. Now we use depth first search to traverse over the tree. Suppose we are at current node src, so we have a base case that src is a leaf. In this case, we can say that dp of src, color of src, and let us say that we do not toggle, which is 0. So the number of steps that we do is just 0. Else if we toggle, then this is gets updated by 1. So we can write src and over here we will do XOR 1. Because if it is 0, it will get converted to 1, else it will get converted to 0. For toggle we write 1, and this is the number of steps that we do is 1, hence we write 1. Now over here we have our recursive case. So for all color and for all toggle, we will iterate over all the childs and we will calculate the answer for dpsrcc toggle depending upon the values of its children. Now let us look at how to calculate dpsrcc toggle in order of n. This solution has been implemented by the editorialist. We start with two vectors, chosen child state and other child state. Chosen child state stores all the children that have been included in our answer, and other child state includes the rest of the children. Now we iterate over all the children of SRC. Basically, we will choose whichever is the minimum of dp child toggle 0 or dp child toggle 1. We will append them into our corresponding vectors. The only difference is that we will use this variable parity to tell us the number of children that have been toggled. Basically tell us whether even number have been toggled or odd. Now if this parity is not equal to the required child parity, we will find the minimum of other child state I and chosen child state I. This is basically the extra costs that we will incur if we transfer a child of the other parity into our chosen child state. Basically, it means that let us say the required parity is 0 and the final parity that we get is 1. Then if we had chosen dp of child toggle 0, then we will delete this from the chosen child state and add other dp of child toggle 1 into the chosen child state from other child state. So we add one more child which has been toggled. So this parity will change 1 XOR 1, which is equal to 0, and now required is equal to the final. The same can be said for if we had chosen dp of child toggle 1. Then in this case we will remove a child that had been toggled. So the final parity will change from 1 to 0. So finally we will calculate the answer as dp of src c toggle is equal to summation of chosen child state. Now let us look at another way to calculate dp of srcc toggle in order n log n. This is an easy to implement solution. Now we will use a vector value to store dp of child toggle 1 minus dp of child toggle 0. This means that we will basically store the extra cost that we will incur if we had taken a child that had been toggled instead of a child that had not been toggled. Now we will iterate over all children of SRC and we will basically add dp of child toggle 0 into our answer. This means that we will not choose any children that had been toggled. This will help us to determine the final parity, as since we did not choose any children that had been toggled, the final parity is going to be 0. We append the difference into the vector value. Now we sort this vector value. If required parity is 1, which means that our final parity is 0 because we did not include any other child that had been toggled, but the required is 1. So we will add value of 0 to our answer. Adding value of 0 here actually means that we will not choose the child with lowest cost that had 0 and we will instead take 1. This means that we are basically including the children that will incur us the minimum cost, the minimum number of steps. Now we will iterate over the rest of the children. So if required parity was 0, we will iterate from 0, and if it is 1, then we will iterate from the index 1, which is the second child. Now we will try to add two children at a time with lowest cost, with lowest extra cost, and if that actually reduces our answer, which can only happen if their sum is less than 0, we will include that into our final answer, else we will just break. Moving on to the code. In the problem we are given t test cases. We will process the input, we will take the color of each node into a vector color, and then we will create a tree. Now if n is 1 and color is equal to 0 of that node, then we will output 0, else we will output 1. We create this 3D vector of dp to calculate our dp states. We will use this function dfs to calculate the values in the dp table. Now the answer is actually the minimum of 100 and 101, which means that the first node can be either not toggled or it can be toggled, and the color has to be 0, of course. If the answer is equal to infinity, then we output -1, else we will output our original answer. Moving on to the dfs function. First, we have the base case, that is, if the current node is a leaf node. In this case, we will assign 0 and 1 accordingly, whether if we have toggled or not. Now we will use this for loop to calculate the answer for the children first. Basically, we use a bottom approach, hence the answer for children has to be calculated first. Now we will calculate the answer for the current node. So first we will calculate required parity. This is calculated as color SRC XOR state XOR toggle. Now we will use these vector values to store the difference between dp child toggle 1 and dp child toggle 0. This is basically the extra cost that we will incur. Now we will iterate over all the childs and we will add dp child toggle 0 to our answer. Finally, we will sort the vector values, and if the required parity is 1, we will add values of 0, meaning we will add the minimum cost to our answer such that we take child toggle 1 instead of child toggle 0. Finally, we will try to add 2 children at a time to our answer such that the parity does not change, and if it actually reduces our answer indicated by sum less than 0, then we will add it to our answer, else we will just break. So guys, this is pretty much the whole code. Try to code it yourself, and if you face an issue, then come back and see it again. So guys, I hope you understood the problem clearly. If you have any questions, drop a comment in the comment section, like the video, and don't forget to subscribe to get our latest updates from CodeChef. Thank you and goodbye.